All right, so let's derive the parallel axis theorem. Because a lot of the ones we've done already, so we did the moment of inertia of a sphere, solid sphere, a hollow sphere, of a hoop, of a disk. All of those are rotating about its center of mass. And so what happens if it's not rotating about the center of mass? So if I had a hoop right here rotating about an axis like that, so that it's spinning around an axis. So the equivalent, since this is the hoop I have at the moment, this is spinning about not the center, but it's spinning about something like that. That is really poorly demonstrated, but let's hope you got the idea. So this is when you bring in the parallel axis theorem. So I've defined the center of mass of this blob right here, and the axis of rotation is not at the center of mass. I have a vector going from the axis of rotation to my center of mass, which is d. I have this differential of a mass right here from that is a vector ri prime from the center of mass and ri from the axis of rotation. And so if I take my vector d plus ri prime, I'm going to get ri. Because ultimately, when you're dealing with the moment of inertia is equal to dmr squared, this r right here is the distance from the axis of rotation to where the mass is. So this is my, what I've labeled as r sub I there. I guess I don't have to do r sub I, I can just do r. And so this becomes the integral of dm times d plus r prime squared, which is the integral of dm times d squared, basically doing a dot product with itself, d squared plus 2d dot r prime plus r prime squared, which is the integral of d squared dm plus 2d dot r, let's go ahead and throw the integral in there, dot r prime dm plus r prime squared dm. D is a constant because those are two fixed places here. And so we have integral of d squared dm plus 2d dot r prime dm plus r prime squared dm. All right, so this right here, this term right here is the easiest one to get rid of. It's the one we can rationalize getting rid of. Because this integral of r dm, this is the sum of the distance to each mass throughout the whole thing. It's not squared here. So what we're left with here is anything on the positive side will get a positive result, on the negative side will get a negative result. In essence, this is how you actually find center of mass. And so since r prime is based upon where my center of mass is, that's the vector from the center of mass, this actually will end up being 0. So my moment of inertia simplifies down to d squared, this distance here, dm, plus integral of r prime squared dm. Now this is a constant here, so this becomes d squared times the mass of the blob, plus this bit right here, integral of r prime squared dm. And this integral of r prime squared dm is just the moment of inertia about the center of mass. And so what we're left with here is the moment of inertia about some axis of rotation is equal to the moment of inertia about the center of mass plus the distance to the actual axis times the total mass. We can apply that. So since we've already done let's take the sphere rotating about this right here, solid sphere. Rotating about that point right here. I know that the axis around the center of mass is, for a solid sphere, 2/5 mr squared. I have moved the axis. The axis is not here. The axis is here. This is my distance d, which is just the radius of the sphere. So the moment of inertia about this axis right here, I'll call that A, is going to be equal to the moment of inertia of the center of mass plus md squared, which is 2/5 mr squared plus m times r squared. So this becomes 7/5 mr squared. Another classic is if I take a really thin rod here, that about the center is 1/12 ml squared, where this is the length. If I rotate it instead of about this point right here, this becomes about, so that's my axis A there. It becomes 1/12 ml squared plus the mass times the distance that the axis moved, which is 1/2 L squared. So this becomes 1/12 ml squared plus 1/4 ml squared, which is 1/12 plus 1/4 ml squared, which is, so common denominator, so 3/12 plus 1/12 is 4/12 or 1/3 ml squared. And so these are some classic examples.